By the way, what happened is a very good example of very bad user interaction. I'm serious. I mean, come on, Apple, do better. Yeah, there's the mother of all demos. A quick aside, seeing as I've been distracted anyway, I may as well get distracted properly. I just ordered a bunch of these to use in the class. So hopefully they'll arrive this week or maybe early next week. So yeah, they're called X-Touch Minis, and they're basically MIDI controllers that you can use to control your assignments if you want to. So they provide you with a bunch of buttons and a bunch of knobs and a slider that you can use to map to pretty much anything you want in your processing application. And we'll talk about how to do that another time. But I just thought I'd flag that as well as the Kinect cameras and the Leap Motion we already have. Okay, so Minority Report. The futurists were asked to come up with the interface of the future, and this is what they dreamt up.
Separate perimeter tunnel on road. I'm placing you under arrest for future murder, Sarah Marks. Superman said. The future can be seen. All we have to run on are the images that they produce. We see what they see. There's been murder in 6 years. There's nothing wrong with the system. It is perfect. I agree. Murder can be stopped. Tell me exactly what it is you're looking for. Flaws. Do we get any false positives? We are arresting individuals who've broken no law. But they would. The fact that you prevented from happening doesn't change the fact that it was going to happen. The system can't be wrong. You said something, Chief? No. You're in a lot of trouble, John. I have a warrant in my pocket that says murder. Don't run it. You don't have to chase me. From 20th Century Fox. He set me up. He set me up.
Oh, come on.
Who's the victim? I've never heard of him, but I'm supposed to kill him in less than 36 hours. He's going to get it. Tom Cruise. I need your help. You contain information I need to know how to get. In a Steven Spielberg film. I have to know. I have to find out what happened to my wife. You tell me, who was it who set this up? I don't know. How about now? On June 21st, everybody runs.
Oh, great. Okay, so the bit I actually wanted to show you lasted for about 2 seconds. This bit.
One female. Killer's male, white 40. Separate perimeter tunnel on road. Flip side, one male, one female. Killer's.
Okay, so he's using his hands. I kind of missed that at the beginning and I was waiting for it to come up. We didn't need to watch the whole trailer. He was using his hands to grab objects, move them around, play videos, stuff like this. So this was like the vision of the future of interaction back when Minority Report was made. I don't know exactly when, around about 2000, I guess. And it's amazing how often science fiction visions drive the future of technology. It's always happening. And if any of you are aware, the iPad, I think Apple sued Samsung for copying the idea of a tablet PC with multi-touch interaction, and they lost because Samsung was able to argue, no, the vision for that has been around since at least 1969, when the 2001 A Space Odyssey film showed the iPad being used, or a mock-up of the iPad being used by the astronauts on a space station. So if you want to see how things are going to be in the future, look to sci-fi, because those visions kind of permeate the society and tend to drive people in, like researchers and everyone else, drive their vision. Other good movies to check out, or a series to check out, is Black Mirror, I think it's called. It's another good one, which looks ahead around about 10, 15 years. Anyway, I digress. So all of that was leading us towards, the vision has been for a long time towards much more gestural embodied interaction, and that leads us technically to motion capture So if we're going to somehow be able to do Minority Report stuff like this and interact with computers by gesture, we need a way to track gesture and get that gesture information into data that we can feed into the computer that we can then map to various things that the computer does. So motion capture systems have been around since the 70s, but in the 70s they were cumbersome, mega expensive, and probably owned by the US military and places like that. Since then they've become more and more, they've improved and become more ubiquitous. Broadly speaking, there's a couple of different kinds. There's optical motion capture systems which work by tracking markers. Well, there's markerless systems, and there's systems that need markers and there's systems that don't need markers. The ones that are more accurate tend to use markers, speaking very generally. And so the markers are basically little sort of ping pong ball type things that are stuck on the body. And when the body moves, the computer tracks those markers using a very high speed camera. And if you put lots of cameras together and surround the person with these cameras, you can get really a full three-dimensional data. You can get three-dimensional data describing exactly where all the parts of their body are at any given moment. So that's optical systems that use cameras, and some of them use markers and some don't. There's also non-optical systems that don't use cameras. They use other kinds of devices like accelerometers that measure acceleration, gyroscopes that measure orientation, and compasses that measure also orientation but in a different way. And an example of that, a commercial product that's an example of that, is this suit here, the XSense MVN. There are others as well, but that's just one that we happen to have at the university that I have played with. And so you can, if you look very closely, you can kind of see on this suit, there's these little sort of square boxy things at various points of the body, on the knee there and on the wrist. They contain the gyroscopes and accelerometers and compasses, and they all connect to a big sort of pack that's on the back. That pack connects wirelessly to a computer, and it's sending the data in real time exactly where all the parts of the body are. And so, they would work in an area probably about as big as this room, wirelessly. So you could say have them on a basketball court and be tracking the movements of a basketballer, and on your computer screen you'll see kind of like a stick figure moving at exactly the same time in the same way as the basketballer is moving. So they're pretty cool. They're very expensive, and they're also quite cumbersome to set up and use. If it's not a question of just kind of sticking the suit on and off you go. There's a lot of calibration and messing around that goes with it. But they do, once you've done that, they do work very well. And they're used by places like Animal Logic and sort of big animation houses for creating animations, for example, amongst other things. But for the average person, if you want to mess around with motion capture and full body interaction, the easiest and cheapest way for you to get into it and start playing with it is using the camera that's down there, the Microsoft Kinect, which costs around about, I don't know if, actually they're getting harder to buy now because they're kind of somewhat old technology in some ways. The version of the Kinect we got there was around about $180 a couple of years ago. They came out in late 2010, and there's drivers so that you can access the data from them for Mac and PC. And what's actually in them is a infrared camera, a standard camera, and an infrared laser. I'll just see if I can move without dragging half my desk with me. Let's try this. That's not really very helpful at all, is it? It's better, somewhat better. It's hopeless. Okay, you can see there's 3 openings at the front, hopefully. One of them is a regular camera, like a normal webcam type camera. One of them is an infrared laser that's actually sending out an infrared signal into the room now. And the other one is an infrared camera. So it's, again, kind of a regular webcam, but it only sees infrared light. So it only sees basically the reflections from the infrared laser that is transmitting out into the room, or any other infrared light that happens to be in the room from sunlight or some kinds of lights. And it uses those cameras and the laser very cleverly to provide us with 3D motion tracking. So what you'll do when you're using the Kinect, if you're using the skeleton tracking mode, it will send out a stream of data which describes the coordinates of all the parts of your body. So you'll get X, Y, Z position of the hand, elbow, shoulder, neck, head, etc., knees and feet. And that'll be constantly fed from the Kinect camera into your processing sketch. So you get this constant stream of data. Again, it happens 30 times a second. I think the Kinect runs at 30 frames per second. So you get, for $180, you get quite a lot. So before the Kinect came out, to get that kind of accuracy and ease of use, you'd be spending $20,000 plus. Out of interest, it uses structured light. So I mentioned it has a laser, and you don't really need to know the details of this, but it projects a special pattern out onto the scene that it's looking at. You could think of it as being like a checkerboard pattern. It's a bit more complicated than that, but if you imagine it being like a checkerboard grid, it's projecting onto the scene. And you can imagine if you project a checkerboard pattern sort of onto me standing in front of this wall, where the checkerboard pattern is on the wall, it's all quite regular. But when it gets to my body, the checkerboard sort of starts to bulge outwards because I'm closer to the camera than the wall is. And so it's got very clever maths and stuff inside that can sort of figure out the degree of bend in each of those lines, and from that can figure out where I am in 3 dimensions. So it can figure out that I'm, a meter in front of the wall, for example, and that this thing is another half a meter in front of me. And so so when you connect to the Kinect camera, you're getting a constant stream of data that tells you where these things are and how far away they are. So yeah, it's a pretty clever piece of gear, really. So yeah, I think I've said that. You can access, on the Kinect, you can access the infrared and the normal camera output. You get a 3D depth map, which looks like this, which is and basically different color pixels at different distances from the camera. So in this case, I'm not sure how the colors are actually mapped, but in this case, it looks like red pixels are closer to the camera than, orange pixels, for example, and blue is further back again. Speaking very practically, how do you actually get this to work in processing? It's slightly more complicated than it used to be because Apple, who just forced me to reboot my computer, also bought Simple OpenNI, which is a nice library that was available for processing to access the Kinect. So Apple bought it and then promptly shut it down. And at the moment you can still get it, but it's a bit sort of tricky to figure out whether it's going to be available in the future or whether Apple's going to kill it or whether they're going to release something else. So we don't know. At the moment it still works and we'll be using it in the lab. And the other option is, so Simple OpenNI is one sort of set of libraries you can use in processing to access the Kinect. And OpenConnect is another one, but it doesn't provide you with a skeleton tracking, but it provides you with a bunch of other features instead. But the advantage of it is that it's current and it's working with processing 3 and it kind of has a more clear future, I guess. But you can sort of choose, if you think you want to go down the gestural interaction path for your project, you can choose one of those libraries depending on what your requirements are, and you just have to mess around with both of them and see which is the best fit. Okay, so I think I've already explained skeleton tracking. This slide is just to point out that one limitation of the Kinect is it has a limited range. So it only works for maybe 5 meters in front of the camera. So you couldn't sort of track movement of someone up the back of the room if the camera was down the front. If you want a larger range, you have to spend $20,000, $30,000 and get one of those X-Sense MVN suits I showed you earlier, or one of the fancy optical systems. The other thing about the Kinect that you will probably find when you start messing around with it is that the lighting in the room can mess with it. Sunlight contains a lot of infrared, for example, so if you're in a room that's got lots of sunlight in it, or if you try and use the Kinect outside, you can get very unpredictable results. You can't always track the movement very accurately. Also, if you would say using it for dancing or something like that, If you're standing in front of it like more or less like a normal person stands most of the time, then it will have not much trouble tracking you. But if you kind of do odd poses or stand on your head or kind of lie down on the floor, it'll start to freak out because it can no longer really find the body shape in what it's seeing. So there's just a few caveats, but it still works pretty well. So what I'll quickly do is just bring up a processing sketch that accesses the Kinect and hopefully demo it. And you'll notice we normally use processing version 3, but for simple OpenNI, that first library I mentioned that Apple just bought and is trying to shut down or do something with, that one only works with processing 2. So you have to download processing version 2 and simple OpenNI and then play with it. It's not actually as big a deal as it sounds because the differences between processing 2 and 3 are not actually that great. But it's a relatively minor inconvenience. So what we have here is a sketch. It instantiates a new simple OpenNI object that lets us talk to the Kinect. You don't have to understand all this code. I'm just going to skip down to the interesting bits. What you can see here is me getting the position of the head from the Kinect and drawing a circle at that position. And then doing the same thing for the left shoulder, right shoulder, torso, left hand, right hand, and so on. And really there's only a few lines of code. Again, you don't need to understand all of this right now. The detail's not that important, but there really are only a few lines of code that you need to use to get the the position of different body parts from the Kinect. So with maybe 20 or 30 lines of code, you can kind of draw a skeleton on the screen, which reflects the movement of someone in front of the Kinect. So let me see if I can demo this without strangling myself. Put that down there. So at the moment, it's not seeing any person, and hopefully when I start to move in front of it, there we go. You can see it's now tracking my body. So when I move my hand up and down, can't quite see my head. There we go. Pretty cool stuff. So you'll be doing all this in the lab tonight. So you can see with a relatively small amount of processing code, you can actually get pretty reliable and accurate motion tracking out of the Kinect. More or less plug and play. Not quite, but mostly. And obviously you should do more, you will do more with this than just draw a cool stick figure on the screen, although that is cool. But you should be thinking about other ways you can link this motion to interaction. So there's one example. I did another example which is on UTS Online and you can mess with in the lab, which more or less does the same thing, but instead of drawing with blocks and circles, I think I used curves from the lecture the other week. There we go. So now we have a different looking animation. But okay, are there any questions about that? And you can see it starts to try and guess where the person is, and it often gets confused. Which is why if you're using it with a dancer or something, it often does weird things. I don't feel like I'm doing that, but here I am. Are there any questions about that? I should check Slido, I suppose. Just Okay, good. Look at maintaining the... Okay, so if you want to do motion tracking in your application, you have a few different choices. One choice is the skeleton tracking, like I just showed you, where you're tracking the movement of all sort of different parts of the body. But there are other options. Rather than, if you don't need to track the whole body, but maybe you only need to track the hands or something else, you could use other techniques, such as blob tracking. And I do talk a bit more about this in depth in future weeks. But I can show you a quick video that demonstrates that. So there's a there's an application here which is basically looking for pixels that are kind of skin colored, or the color of his hand anyway, and where it finds pixels that color, it kind of will track them. So it finds that there's a bunch of pixels that are kind of like at certain XY positions, and we're going to track those. So this is generally more reliable than skeleton tracking. So with skeleton tracking, the Kinect camera and the software is trying desperately to fit whatever it's seeing with the shape of the human body. With blob tracking, it's sort of technically simpler and generally more robust. As long as there's a pixel in a particular color range, or there's enough pixels in a particular color range, it will track the movement of that interaction.
Wouldn't there be a problem with blob tracking if you have people of different skin colors? I remember seeing a video, I think it was HP was trying to detect, HP computers were trying to detect faces, and they didn't test it on any African American people.
Yes, yep.
And the accusation is that HP computers are racist.
Yeah, yeah. So, yeah, I mean, obviously you have to be careful whatever assumptions you're making, you know, and yeah, you would have to be careful, you know, there's obviously a range of skin tones out there in the world. If you want your application to work reliably, you're going to need to take that into account and make sure your app deals with it. So yes, that's a very good point. But there might be other ways around that. So rather than tracking skin tones, you might give the users a torch, for example, or a light, something like that, or something like a piece of cardboard of a particular color, and track that instead. That way you know what the color is. You know, if you're tracking a red piece of cardboard, you know exactly what the color of that red is, and you can track it. You don't have to worry about what the user looks like. If you want to go even more lower tech, because you're worried about maybe sort of skin tones tricking your tracking software, or you're worried that the different lighting will change the colors that you're tracking of the blobs, which it will. Lighting changes things massively. Then you could go for another tracking approach, which is optical flow. And in this approach, all the software is tracking is the movement of pixels. So it looks for it between two frames of video. It looks at the first frame and it finds, okay, there's the color, the pixel here has a particular color, and then it looks in the next frame of video to find where is the pixel of that same color. And if it finds that it's say 5 pixels further to the right than it was in this in the first frame, it says yes, this pixel has moved over 5 pixels to the right. And it does that for every pixel in the frame. So basically, wherever there is a movement of pixels between one video frame to the next, optical flow will tell you that. Let me bring up an example from an application we actually used for one of the performances we did recently. Okay, so this is a optical flow tracking system that we developed for a dance performance where we had to track the movement of performers. Skeleton tracking was not going to work because the performers were going to move in a much bigger area than 5 meters, plus because the dancers were moving in different, were moving their body around into very strange shapes. Skeleton tracking would get mixed up. Blob tracking wasn't reliable because we couldn't reliably we didn't reliably know what the colors of the pixels were going to be. The colors of the performers were going to be wearing. So we used optical flow so that we knew that any movement on the stage at all, we could track. So whenever there was movement of pixels on the stage, it could be because performers were moving or because some object was moving on the stage, we would track it. So what this does, this tracking software takes the camera feed from my laptop, and over here, you can see it's drawing these little white lines. That's more or less just from noise, like from image noise. But when I move my hand, you'll see there's a lot of bigger white lines. So that's showing the movement of the pixels of my hand. So each one of those white lines represents the amount of movement of that particular pixel, I guess you could say. So the advantage of this is that it doesn't matter, it's very low tech. As long as something moves in front of the camera, this will feed that movement into the computer. But you won't know what that movement is. You won't know whether it's someone's hand or their elbow or their head or anything else. You'll just know something moved at this sort of region of the image. So all these things are kind of trade-offs. Is there any questions about that? Does that kind of make sense? So you've got skeleton tracking, very cool, but more flaky and less reliable, only works with a limited range. Blob tracking, more reliable, but still relies on having some control over the quality of the image coming into the camera and the colors that are in it. And optical flow can track anything that moves, but doesn't really give you any information about those things that are moving. Okay, so another bit of hardware that you can play with and that we have for you to borrow in this subject is the Leap Motion. They'll be in the lab tonight, and for this week, but we're going to be focusing on the Kinect to start with, just to sort of limit our battles. But if you kind of get the Kinect running and you want to play with something else, try the Leap Motion. It's a tiny little device, as you'll see, about so big. It sits on the desk usually, and if you move your hands above it, you can track the movement of your hands and also each individual finger with quite high precision. So you don't get full body tracking, but you do get very precise hand tracking, much more precise than you would get out of the Kinect. So we'll play with those as well. That gives you another tool for your toolbox, I suppose, to use. So the question is, okay, so we can get all this information in. What now can we do with it? What's interesting, useful, what's interesting or useful or inspiring to do with this technology? Science fiction has given us lots of visions of interacting with computers by moving our hands around, but the Kinect's been out now for 5 years or so, and there's no one in here interacting with their computer by waving their hands around in front of it. So the question is, why not? Why didn't we go down that road and develop applications that use Minority Report style interaction? So it's not so good for desktop computing, at least we haven't figured out a way to make it work effectively so far. But it might be good for animation, like virtual puppetry. It's been used a lot for games, although again, I don't know to what degree it's really been as successful as Microsoft hoped in terms of games. We could use it for music or dance, and there's lots of examples on the web and elsewhere. Maybe for security somehow, if it can, I don't know, track movement of people, detect intruders and things like this. Or biomechanics, looking at the movement of sports people or dancers to try and understand more about how they move or how they should move, for example. So
Hi, I'm Theo Wilson, and this is Emily Dozier, and we're just going to show you a little prototype of something we've been working on with Microsoft Kinect.
here's one kind of.
Sort of like an interactive, like
I'll turn the audio off. So, virtual puppetry is kind of a neat idea. So motion capture has been used a long time in animation. Why not use the Kinect to sort of do virtual puppetry? What kind of possibilities does that open up? And yeah, this is quite a well-executed example that works pretty well, actually. But to what extent is it usable beyond kind of a cool demo? I'm not sure. So I'll sort of finish up with some tips for using motion tracking. I'll say that in general, motion tracking works best if you have continuous links between the gesture and the sound and the visuals you're producing. So what tends not to work is if you sort of say, okay, well, when we're going to make a musical instrument, and when I put my hand here, it's going to make a ding sound, and when I put my hand here, it's going to make a doof sound, and I can go ding, doof, ding, doof. And that superficially might sound like a good idea, but it tends not to work in practice. Can anyone tell me why it might not work so well in practice?
It wouldn't recognize every single time necessarily.
Because it doesn't recognize every single time necessarily, so reliability is definitely a problem. If you go ding, 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 that very quickly gets frustrating for the user. So reliability is one reason. Any other reasons?
You can't really vary the kind of sounds you're making. You can't go.
Yeah, you can't really vary the kinds of sounds you're making. So whether I go like this or like that, it's still going to trigger the same ding sound. Ding, ding, ding. So it tends not to be very satisfying for the user. We can say that from experience, and there's been quite a lot of research that shows this as well. Could we just have, if you guys up the back don't mind keeping it quiet, if you need to talk, could someone just grab their attention? Hey, if you need to leave, I don't mind, I won't be offended, but just keep it down so people can hear if they want. So if you're going to need to trigger sounds, like you want to make a sound that goes ding, ding, doof, doof, that's fine, but motion capture is probably not a good way to do it. You would be better off with something like that, for example, that has buttons that when you hit the button, it creates a ding and another button creates a doof. You can also use like a monome type interaction, which a lot of DJs use, which, each button, there's a grid of sort of 64 buttons. Each one triggers a different sound, and that can work quite well. It's more reliable, and it's sort of it seems a more natural interaction for that kind of thing. So if you have discrete links, if you want to trigger discrete events, like the single playback of a note or the single trigger of a drum sample, you're probably better off using some kind of button, whether it's a virtual button triggered on the screen or an actual physical button. It's up to you. The virtual buttons where you use the leap or the connect to kind of go like this to trigger a sound, like push a virtual button, as was mentioned before, they tend to be not very reliable. And you'll get the user kind of going, okay, yeah, I want to trigger that sound, or I want to go to the next level. And they do it once, and then nothing happens, and they kind of go like that again, and then they start to go like this, and eventually it works. And it's really just because of changes in lighting, this posture that they have that kind of fools the computer and makes it not work so well. So just to be clear what I mean by continuous links between input data from the user and output, a continuous link, if in terms of a graph, would look something like this. If what's down here, say, is the x coordinate of your hand, moving like this crossways, horizontally. And if what's up here is, say, the volume of a note, then as I go like this, the volume increases. And so I have a note playing continuously, and as I go from your left to right, it gets louder and softer like that. So there's a continuous link between your gesture and the sound. It's not bing, 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 being triggered by certain sort of imaginary hotspots. So those kinds of links work better with gestural interaction, as opposed to this discrete interaction where, as I said, as you move across, you're triggering events, and it could be sounds or it could be visuals or anything else, but you're triggering some kind of event only at certain points. So that is not such a good fit for gestural interaction, but is a good fit for buttons and other types of interactions. I think I've said before in one of the earlier sessions that if you're designing for any kind of interaction, really that you're designing, in this case, a kind of interactive virtual musical instrument, ultimately what you're concerned about is mapping the input gesture or the data that reflects that input gesture to output somehow or other. It's all about mapping. So this diagram is just really attempting to show you that we have gestures coming in from the user, being sensed by some gestural controller like the Kinect or the Leap Motion or a camera. And from that we're getting, coordinates of hands and feet or whatever it is, but we're getting some kind of data that reflects those gestures. And in our program we're saying, okay, well, the X position of the hand maps to the volume of the sound. So that's one mapping. Or the Y position of the hand maps to the pitch of the sound. So designing a virtual musical instrument is all about those mappings. And for gestural controllers, what the research shows generally is that complex and cross-coupled mappings are usually perceived by the user as being more expressive. So if you want to make an expressive musical instrument, make it complex and cross-coupled. And what do I mean by that? If you think about someone playing the trombone or a clarinet or any other kind of traditional acoustic instrument, if you play a trombone pianissimo, really soft, and then you gradually get louder until you're playing the loudest possible note you can play, what changes is not just the volume. The trombonist might just be playing, a B flat or something like that. But as they get louder, what's changing is not just the volume. A loud B flat sounds different to a soft B flat in more ways than just the difference between soft and loud. The timbre, the tone of the note actually changes as well, and often the pitch of the note might change a little bit as well, depending on how good the trombonist is. So the musician is working with this instrument. The instrument has a tendency to kind of cross-couple things. So as you're increasing the airflow into the trombone, the pitch of the sound is tending to change, the volume is tending to change, and a whole lot of things are changing at the same time. So faster air doesn't just mean louder note, it means a bunch of other things. So in computer terms, you'd say airspeed maps to volume, but also pitch and tone. So you might think if you're doing a gestural instrument, it might map to something. It might mean you do something like this. Your hand Y coordinate or your hand X coordinate maps to pitch primarily, but maybe also to volume, and also to timbre, to tone. Sorry. Or your hand Y coordinate might map in visual terms to colour, but also brightness. So if you want to make an expressive audiovisual instrument, you're going to want to look at complex cross couplings between your input gestures and the output sound and visuals of the computer. Complexity is going to generally make people perceive your instrument as being more expressive. If you make it too complex, then they'll perceive it as being random. So it's all about finding that sweet spot between complex, but not so complex that when they move their hand, the computer does everything, and people just perceive no kind of relationship really between their gesture and what the computer's doing. So that's the challenge. And that's why I made it one of the options for the assignment. I'm going to call it a day there because we've got the next class coming in, and I think I'm more or less finished anyway, but if you look at the slides, you'll see there's some links to some projects, again, to give you more ideas for your assignments. And that's it.